In this video, we'll discuss the concept of continuity of a function and why it may be important with limits and so on. So a function is continuous at a point, say x equals to a or some number, if the following three conditions are satisfied. Well, first of all, f of a has to be defined, or it has to be an actual value, so you cannot have a hole there, for example. Number two, the limit as x approaches a of f of x exists. So you cannot have another type of discontinuity, you'll see later. And the third one is that the limit not only it exists as x approaches a, but it actually equals to the y value at that point. So let's take a look at some examples when at least one of these conditions is not satisfied. Then of course you have a function that's not continuous. What kind of discontinuities can we have? Well, there's three cases that we will observe quite regularly. One is a jump discontinuity. This frequently happens with piecewise functions, or if you have a function that's composed of more than one piece. For example, in this case, notice how you have a hole on one side and a filled-in point on another. Well, actually, you do have a y value right at this filled-in point right here. So f of a is defined, but there is another problem. The limit does not exist because if you recall, if we're approaching from the left, we're approaching the hole, so we're approaching one value. And if we're approaching from the right, we're approaching another y value. So the limit does not exist, and that's why it's not continuous. So this is called the jump discontinuity. Then we can also have a hole in a function, which we've noticed if you have a single equation, but you have denominator that can cancel with numerator. So the limit does exist. Notice from left and right, we're approaching the same y value that's at the hole, but there is a problem. F of excuse me, f of a is not defined, or if it is defined, it could be somewhere else, could be above or below the point, and it would certainly not equal to the limit in that case. And third situation we can have is a vertical asymptote, which is sometimes called the permanent discontinuity, that the limit either does not exist if you have both sides approaching to different infinities, or is infinite, which in that case it still does not equal to the y value, even if it's defined. It could be somewhere on the asymptote. You can define it anything you want, but it still would not equal to, because the y value has to be finite, not infinite. So first we'll practice finding any values where the function is not continuous. Some of them are pretty obvious, but for each point of discontinuity we must find limit as x approaches from the left, limit as x approaches from the right, and then the actual two-sided limit if it exists, and then f of a if defined. And for the last part, we must identify which condition is not satisfied, if any. So sometimes it's more than one condition, so we have to satisfy the main one, or I guess the first one that's not satisfied. So let's take a look at the first example. Notice it's a jump discontinuity. So let's take a look. The limit from the left, notice how we're approaching the y value of 2. But from the right, we're approaching the y value of 4, right where the hole is. So the two sides, let's take a look, do not match. So that was our a value, by the way, x equals to -1. So the limit does not exist. The f of -1, if we go back and look at the graph, was the filled-in value, which was 2. But the main condition why it was not continuous is that the limit did not exist. Okay, certainly if it does not exist, it would not equal to the y value, but the main condition is that it does not exist. Okay, now let's take a look at another example. Same kind of situation, but here we have, note how we have a hole on the graph at x equals -2. That's why I mentioned a equals -2. Now let's take a look what the limits are equal of. From the left and from the right, we both approach y value of -1. So they do match, so that means the limit exists and it's -1. But the problem is f of -2 is not defined. That's the very first condition. So the condition that's not satisfied is that f of -2 is not defined. Now let's take a look at the equation situation. So what if we have the equation of f of x equals to 5 plus x over x times x minus 2? Notice the function is not continuous where denominator is 0. It's also not defined there. So at x equals 0 and x equals 2, Both values are vertical asymptotes because you cannot cancel it from the top. The limit does not exist for both values. How I figured that out, I graphed it, and at both of those vertical asymptotes, both sides, the left and the right, were approaching different infinities. So if you graph it, you will see it. It approaches, I think, negative infinity on one side and positive infinity on the other. So this is how you can figure out that the limit does not exist. You can graph it, and if both sides go to different infinities, it does not exist. Now notice in part B, it was a whole because you can cancel it with the top if you factor it. If it is a whole, you can find the limit at that value. How do we do it? Well, we did it in the previous section. You cancel it. Notice how we keep the limit, to keep writing it until you are ready to plug it in. Okay, so by definition, the limit of f of x is equal to f of a if it's continuous. So we do keep the limit until we're ready to plug it in, and notice how as soon as we plug it in, I do not write the limit anymore. So pay attention to notation, how you write it, because it's very important in this case. So again, while we're simplifying, I keep the limit. As soon as I plug it in, I do not write the limit anymore. So it may be important for the assignments later if we have it. Now the third example, it's a polynomial, x squared minus 4x plus 11. Notice how we discussed in previous section that polynomials are continuous and there is no denominator that you see it. So it's continuous for all x, or for all real values. There is no point of discontinuity, so you cannot answer any of further questions. So f of x is continuous everywhere on the real line. Next, let's discuss piecewise functions. As we can see, there's a lot of jump discontinuities that can happen. Let's take a look at this one that's composed of 3 pieces. Now notice you can graph it by hand, which typically what I do is I subdivide the graph at 2 and the 4. I draw like the little vertical lines or the dividers, which I erase later. And then I make a table for values. For example, for 1, it would be x less than 2. It would be x plus 3. I usually would plug in 2, 3, and 4, all the way up to 4. So I do the endpoints also. And then 7, I would start with 4, even if it's greater than 4. It would just be a whole wherever it's greater, and then I would proceed with further values. So you can also graph it on the graphing calculator using this code right here. So notice you multiply the piece of a function by the inequality, and you can get the inequality symbols by pressing second then math, which will take you to the test menu, and it will have the inequalities for you. You do have to know where the holes and the filled in values are. That's very important because on the calculator it will either look solid or sometimes it will join the pieces depending on which calculator you have. You can also graph it on Desmos if you prefer that. Sometimes I do because it's easier to see. You can do the condition first, then a function, condition, then a function, condition, and so on. Notice how on TI, the conditions, these two, you have to break them up. If you keep them together, you probably get a different function, so you have to break up the continuous x's between 2 and 4. But with Desmos you do not have to. That's kind of a nice thing. But let's take a look what the graph looks like. I tried to use the graph from Desmos, but notice it's -1, it's positive 1 up to 2. So it's a horizontal line. Notice how I supplied the whole because it was x less than 2, if you remember the conditions. And it was filled in points. Now notice the whole fell right on top of the filled in point right here because the y values match right at x equals 4 right here. That's why you don't see a hole here. They're both filled in. But on the one, on the other hand, it doesn't fall on top of the filled in point, so you keep it as a whole. So again, remember x was greater than 4, but it fell right on top of that point, so that's why you don't see the hole. But x less than 2, you see the hole there. All right, so the only point of discontinuity was x equals 2, not 4, because it looks continuous there. So the limit from the left is 1, but the limit from the right, you can either try to tell by the y value, it looks like 5, or you can plug it back into the equation x plus 3. If you plug in 2 into the x plus 3, you will get 5. So you need to plug it in into both the left and the right side. The limit does not match, so it was not continuous. Notice here is another piecewise function. Again, I graphed it on graphing calculator and Desmos. Same thing. You had to supply the whole on the x equals -1, because notice it's a strict inequality here. So it ends on the whole on the left. But then it's between -1 and 3 with less than or equal to, so I did put in filled in points. And since the second 11 happened to match with 11 on the x squared plus 3. If you plug in 3, you're going to get 11 there, because it's, oh, wait a second, 3 squared plus 3 is something, I think it's supposed to be 2. I might have made a typo here. Okay, yes, that is supposed to be 2. Let me fix this. Sorry about that. So I'm going to put this 2. Otherwise, it's not going to make sense. Occasionally, there are little typos that do not make sense. So it is 2. Otherwise, they would not match. And of course, it would not be continuous. Okay. So, again, the only point of discontinuity was x equals -1. The right side was 11. The left-hand side was 3. So again, you can either tell it from the graph, looks like 3, or you can plug it in into x squared plus 2, so which would be 3. Okay. Now the last graph only had 2 pieces, so it would be easier to graph on TI-83 or TI-84. Notice they also happen to match, so there are no points of discontinuity. So if there is none, you cannot answer any limit questions. So we just have none. And that's it.